So then, yeah, welcome to my talk. Using TLA Plus to fix a very difficult glibc bug. I'll just jump right into it and explain what these things are. So TLA Plus is a formal specification language. It stands for temporal logic of actions or something, but that doesn't really matter. Yes? There's no microphone, sorry. I can speak up, sorry. Let me speak up. So, okay. Yeah, so TLA Plus is a formal specification language, and mostly it's used for simpler things than glibc. It's mostly used for like protocols or like, I don't know, distributed designs and like and that kind of stuff. And everyone knows what glibc is, at least in this audience. It's used in everything. And the bug that we're talking about is that condition variables would sometimes not wake. And this is an older screenshot, but like it broke in 2017 and was reported in 2020 because people don't update their glibc immediately. The person who reported this said that .NET as a framework was broken when running with glibc, and then other people chimed in saying, hey, Python also broke because of this, and OCaml, and lots of things that use condition variables. And this was like one of those very bad bugs that you just hear about because people talk about it. So what's this condition variable thing? It's one of those like synchronization primitives that you use to build higher level things. You use it when two threads have to like agree on a condition. So one thread needs a list to not be empty before it can continue, and some other thread makes that true. It puts an element in the list. So the first thread says, currently the list is empty, I'm going to go to sleep on the condition variable. The second thread puts an item in the list and then wakes up the first thread. And the bug is that like sometimes this wake didn't actually happen, which obviously can break your code because you want to continue running in thread one. Cool. I'm also just going to summarize the story real quick, just so we all like know what's going to happen. So they had this bug, and there was lots of theories about what was actually causing it, and I was able to prove those like incorrect with TLA Plus, and I was able to actually fix the bug. For some reason, they still preferred somebody else's patch, and I didn't understand that patch. But I was also able to prove that patch correct using I was able to prove and improve that other patch using TLA Plus. And that's now released as of earlier this year, and actually, slide I added today, as of yesterday, it's backported to older versions. So it's gonna be in, I don't actually know which versions, but like yesterday I saw a bunch of emails come in saying patches got accepted to earlier versions. I didn't do that. So it's finally fixed. Cool. And we'll cover condition variables and the bug, and how TLA Plus works, like what its model is, how you translate from glibc, like C code, to TLA Plus, and how you actually fix the bug afterwards. Cool. There's one big doubt that you should have, which is when you try to fix a bug using a different system, like I'm breaking one of the rules of debugging. Like if you have a book like Debugging, one of the things it says is like you should stimulate the failure, but not simulate the failure. So his example is like if you have a leaky window, he was saying like every time it rains, the window leaks. So what you do is you spray your hose at the window so that you don't have to wait for the next rain before you can investigate the issue. You want to like actively work on the bug, but you don't want to spray on a different window. You don't want to say like works on my machine, basically. And what I'm doing when I use TLA Plus is I'm very much spraying at a different window. Like I'm very much simulating the bug. So when you break a rule like this, you have to justify why you do that. And it comes down to that I have got faith that you can basically do everything in TLA Plus. It's a very powerful system, as we will see. If you put enough work into it, you can like simulate anything, and I was confident I could definitely simulate this bug. It's more the question of like how much work is it going to be, and like what do you gain? Because when they reported this bug, they had actually a very good bug report, and it immediately had like a reproduce case where you had a C program that like ran on all your threads, hammering on a condition variable all at once in a second. But like the reproduce case took like many minutes, and if you have multi-threaded code running for many minutes and eventually it hangs, you don't know like what exact sequence of things led to the bug. Yes, question?
Just to clarify, so I understood correctly. So some parts of glibc are not written in C or assembly, but instead written in some third thing called TLA Plus?
No. They're written in C, but I translated them to TLA plus and reproduced the issue there. So I did a translation to TLA plus of that code.
TLA plus is some programming language.
Yes, we will see it in a minute, yes. And so, but what it gives you is, it gives you the shortest interleaving of like threads to reproduce the issue. And so you can see like instead of having to wait 30 minutes and then trying to understand in debugger like what exactly happened, it's going to give you like, here's exactly the like steps that have to happen, like where this thread runs and this thread and this thread. And then it's gonna like show you all the variables along the way that lead to like this bug happening. And it's like very good at finding weird edge cases because it will try all possible interleavings. It goes brute force down the entire tree, and it will find all interleavings that you never even thought about, that are really hard to reason about. And then since it tries everything, it gives you confidence when iterating because you know like all the cases are handled. And when the bug is fixed, you also get confidence in that. With one big asterisk, which is that I initially proved the mitigation patch, which didn't actually work. I proved it correct because I had a test that was too simple. So all you can really do is you can say like in this test, this patch fixes the bug. If I had had a slightly more complicated test, which I had later, then the mitigation patch would have not been enough. We'll talk about that later. And yeah, the reason why it's difficult is because the bug was so rare. Like it took years to even be reported. And they had this very complicated condition variable. And it was complicated because they want to wake roughly in order, which is going to be important later, so I'll just explain. So they had like, in an old design, they had a bug where like thread 1 is sleeping, thread 2 is signaling, and then so you expect thread 1 to wake up now, but if then a third thread comes along and goes to sleep, it could happen that thread 3 would be woken up and thread 1 would stay asleep, which is not strictly disallowed, but it's really weird. Like even if you're sure that this order happened, it was weird that like thread 1 would stay asleep. And so they wanted to fix this, and that's why like the condition variable works very hard to wake things roughly in order. Yes?
Is condition variable supposed to wake up one thread or all of them in this case?
You can choose, but in this case, just wake one thread. But yes, you can say how many you want to be woken up. Well, actually, I think the interface is like wake one or wake all. I think those are the options. Anyways, so when I saw this, like it was bad enough that people were talking about it, and it was, the weird thing was that there was like no urgency on the glibc side at all. So like you get this excellent bug report with like reproduce case and like mitigation patch provided, and the only response they got was like, well, we'll look into it, might take a while. This happened after like months later. And then other people come along saying, hey, Python is broken, and hey, like other languages are broken. And like they just, I don't know, it was kind of weird. I mean, I later learned that like the person who wrote this code wasn't working on condition variables, wasn't working on glibc anymore. So I think there was a bit of a lack of understanding of the code from everyone's side. But
I think the expectation is they're not going to fix it anyhow. Because that really hit us where I was working.
Yeah.
And I was like, well, aren't they going to fix it? They're not going to fix that. So we had to sort of move off that condition variable.
Yes.
Because it was unreliable.
I think everyone, yeah, we did the same thing. I think everyone did that. Just like stopped using glibc condition variables.
Yeah.
But yeah.
I say I wouldn't want to fix it anyway either. So.
Yeah. So yes.
Why did like a company like Microsoft did not try to fix this, given their C# is broken?
I mean, they had submitted a mitigation patch, which people thought was working. But then, I mean, the mitigation patch was ugly and bad, and like everyone agreed it was ugly and bad. Even the people who like submitted it, they were just like, "Here's a hack that makes it work." So it was clear that was never going to be accepted. I don't know, but like, yeah. When I saw this bug, sitting there, it's motivating. like you get a certain anger when someone gives you like a really good reproduce case and people just like don't respond. It's a frustration that like.
Also, when was it introduced? You said introduced.
2017.
2017.
Like, you know, these are people. They look at it, it's like, man, that is a nasty bug and some nasty code. I got other things I could do.
that is my main explanation, which is why I added the second bullet point. Yes. The other thing I had, like my second motivation was I had used, I'd written my own condition variables before just for fun, and I'd verified them in TLA+. and it is just very good at finding all the weird things you never thought about. And I was reminded of the time when I came straight out of college into a job where nobody was using unit tests. And I was like, man, I can show you how to do this much better. Like, you're living in a sad world. Like, there's a better world out there. And like, this was a similar thing. I was like, I can show you a better world. Like, because the reasoning in the bug report was all kinds of like ad hoc, and like people weren't sure what was actually happening. And I was like, no, this is what you should use. This is like, this gives you superpowers when doing like concurrent code. So I put a screenshot of this blog post. Like, is you can make things happen if you're angry about something, which was like part of my motivation. This is like half of my good work comes out of this. I recommend it. So let's talk about TLA plus and how to build things with it. So I'm gonna show just here, like as introduction, a bad spin log. Like, this is a correct spin log, but like it's slow and you shouldn't use it. And then this is what it looks like in PlusCal. PlusCal is a language that ships with TLA plus. It is an imperative layer on top of TLA plus. So it's not like a separate thing, it just ships. Also, there's a global variable on the side somewhere. But let's just walk through this code. So it's pretty much a one-to-one translation. So here's like the function lock, the function unlock. I have to declare my local variables, and I start with this label. And labels work a bit like C labels, like you can go to a label, for example, but like they are very important, and in PlusCal, because labels control atomicity. So there's no atomic exchange in PlusCal, but you can very easily write your own by not putting a label between these two statements. If there's no label between these two statements, they happen at once. So this is my atomic exchange. I just like store the old value in a local variable and set it to true, which is just what happens on the left here. And then since there's no label between them, they happen at once. Like the program counter only ever stops on labels. Yes, question?
So if you put a label, but you never say go to that label, does that also mean non-atomic, or is it atomic if you never go into this?
So when TLA plus explores like the state of possible interleavings, it will stop at every label. Okay. And so like the goto is just like, I'm just telling it like, go back to that label. There's also loops, but I just wanted to show the goto. And then the check is just like, yeah, if the old value, if it was locked, loop, otherwise you have the spin lock. And unlock is the reasonable thing. Let's see. Then you can run that, and you would write like you declare a process. A process is like an independent thread of execution. And there's a lot of things you actually have to explain. So like P is just like the name. It comes out of this global list called proc, which I define somewhere, where I just give like my names. Mostly you use this to like say how many threads you want it to be. We'll see this in a second. And then in a loop, I just call like lock, unlock. The label on the outside is like the label that gets revisited on every loop iteration where you re-evaluate the condition. And then in the middle, I have like this label called CS, which is where you just stop. I just want to stop between these two calls so that like nothing happens there. So like I just get to write checks in the next slide. Another thing is I say this process is fair. Fair means that the process will not stop randomly. So in C++, the thread is always fair. Like it doesn't just stop randomly. So like if it wasn't fair, you could break this very easily because you could like lock and then just leave forever in the middle of the code. But that's why I have to make it fair, otherwise it would break. And the use case for like this is, let me just finish and then I'll take it. The use case for this is like if you write distributed systems or something and you want to like have a like the Paxos algorithm where they have to like multiple machines have to agree on something, and it could happen that one of the machines gets unplugged in the middle and you still want the others to like come to an agreement. Like that's not a fair process. It can just go away at any time and you still want the rest of the algorithm to work. But that's not how C++ threads work, so I just like make them always fair. Yes, question?
Stop, you mean terminate, right?
Yes, it just like, yes.
Not pause.
Not pause, yes. Yeah, it will always pause on every label, yes. And then there's one extra thing, which is like I put a minus behind this loop. It just means like that's the one label that has like exception for this fairness rule. Like, and this is mostly to give you like a sense for like what features are available, like how does this language like think of like what it provides you. And then you can write checks, and the checks you write in TLA plus, which is like not in PlusCal, but like in the language that it compiles to. And TLA plus is written by the person who wrote LaTeX, by Leslie Lamport. So you write it in like this LaTeX-like language, and then you hit a button and you get the nicely formatted code. And so what this means is like for all pairs of processes, like this is just from the same like set that I had on the previous slide, like this set. If it's not the same process twice, then I assert that they're not both in CS, in the critical section. Like the program counter, this is just like, it's not at like this label for 2 threads at the same time. This and, like the conjunction, like it's just the syntax where like if you vertically align the conjunctions, it means like they're all ANDed together. This makes more sense for longer chains, but like you can assert this thing and like it will check this for all possible interleavings and then tell you that either this happens or it doesn't happen. A second thing you can write, this is more powerful, is you can write deadlock freedom. And so what I say is for all processes, if it is at the exchange label, which was the label in the beginning of my log function, then squiggly arrow means at some point in the future, there exists the process in the critical section. Okay, so I can write an assertion saying if this thing happens, then at some point in the future, this other thing has to happen. And it's gonna check that for me. And this is like a very powerful thing where you can like really powerful assertions like this.
So what it's saying is that if my process hits the label called exchange,
yes,
then some other process will hit the label called critical section.
Yes, or the same process, yes. Because this spin lock does not guarantee forward progress. And I'm actually going to go to the demo, so we're going to see like what happens if I change that, and it's going to like show me the interleaving where that's not the case. So this is like the same code in the TLA toolbox. It's literally the same code. Let's just go through it real quick. So this is the code up here in +cal, and then you have to hit a button, it gets translated to TLA plus. So this is the TLA plus language. And so for example, here's like the translation of the exchange label. Let's go back and look at it again. It's like, I store the old value, I set log to true, and then I move on to check. And so down here, the way that TLA plus works is there's, the program counter, and there's also PC prime. And it's always like the old value and the new value. And the new value always has a prime behind it. So like logged prime is true. That's like the new value of logged is true. We're saying if I am at exchange, then old value is the same. Like this is a map. It's indexed by the process because it's a local variable. So each process has their own copy. So it's the same except I overwrite like my own value for logged. And then the program counter is also the same except I move on to check. And like you could write this TLA plus yourself, but you can also just write it in +cal and then like hit the translate button. But like this is actually what the underlying like logic thing is. And as I said, like these vertically aligned ands mean like these all have to be true together. And yeah, the stack doesn't change because we don't do a function call. Like this is just the same, stack prime equals stack. And then down here under all of that, I have my assertions. And so what you do then is you have like this model where, let's see, I say I want both of these asserted. I have to define this proc map where I just give names to the processes. I just call them P0 to 4. So I've got 5 of them. I hit go, and it's going to brute force go through all possible interleavings of all these 5 threads going through these the spin lock. This is a small piece of code, so it takes a few seconds, and we're done. And it just checked that my assertions hold for all these cases. And then like we have this deadlock freedom where like this spin lock does not actually guarantee forward progress, and it could totally happen that like some other thread always gets in your way. And so we can like change this to, actually let's make a copy because it shouldn't have the same name. So let's say I change this so that, hard to modify. I don't know. I actually don't know what the correct name for this is. It has a name, but like let's just call it something like that. If I go back to my model and I say I want to also check this thing, then if I run now, it's going to find the interleaving where that's not the case. And so it takes a few seconds, and then it says, sorry, very small text. I don't know how to make this bigger. It says, temporal properties were violated. And then I get over here on the right, I get like the sequence of states that led to this violation. And so each of these is like one step. If I click once, I get to the TLA plus code. If I control click, I go to the +cal code. And like you can just see like what sequence of like steps led to this happening. And I see here, for example, like the full, like here's what the program counter looked like for each of the process at each state. And I get the full sequence of things, and all the way at the end, it's gonna say I went back to state 7, which means it found a loop where it can loop infinitely without this process getting into the critical section, because some other process always gets in. And if I had like a ticket spin log or something, then it would not be able to find this, because at some point, like because all the processes are fair, so like at some point they have to make progress. So that is this in TLA plus. Any other questions for this part? Yes.
Can you show the forward progress and go to show the forward progress at the requirement that you said added?
Yes. So all I did is I modified it so that, like I said, the process that has to be at critical section at some point in the future is the same. So I just like replaced this with like I used to say that it used to say that like some other process, there exists some process, it can be the same one, can be a different one, but now it says it has to be the same process. And this is not guaranteed by the spin log, because it's like, it just doesn't guarantee that, right?
Yeah,
cool.
What's the intended utility of TLA plus? Like, what is it? Is it designed to be used for this, or?
Yes. Yeah. This is like its only use case. Yeah. People use it to like use it like the. If you go to the website, they have lots of things where people say like, we verified our distributed database protocols with this, or like, I watched some talks from the TLA Plus conference in preparation for this, and like someone had a database replication algorithm that they verified with this, and like one of the Xbox consoles, they verified the caching algorithm, like the hardware cache implementation with TLA Plus. It's like this kind of stuff, basically. Yeah, like, yes. No.
Is there a particular source you'd recommend as either like as a reference for learning TLA plus?
Yes, second to last slide. We'll get there. Good. Cool.
Is it written in LaTeX?
No, it's a video course. I'm going to recommend a video course, but yes. But yes, there's lots of LaTeX in yes, there's. Cool. So after the spin lock, the next thing I want to explain is futexes, because that's how you do anything not spin locky. And so a futex is it's if you don't just want to spin on something, you have to use futexes basically. And they've got two operations. They've got, one of them is compare and wait, and the other one is wake. And what's important is that these are atomic. So it does like an atomic comparison of a state and then waits. And they're famously tricky, but I won't go into that. We'll just show a mutex. So this is a mutex that's like very similar to the spin lock that uses futexes. And this is good code. Feel free to use this. Like, this is a working mutex where I verified this in TLA plus, obviously. And like my goal with this mutex was to only use exchange, never use compare exchange. So we start off the same as a spin lock. We just try to exchange it for locked. And if that succeeds, we just return right away. That's fine. If not, we exchange the state to sleeper, this third state. And then after we exchange it, we call futex wait. And this is so what we pass in, there's two actual arguments. There's this like state and sleeper. And so this is a compare and wait. So what's going to do is going to dereference this pointer that we pass in. And if the value behind the pointer is equal to what I pass in here, then it's going to put my thread to sleep. It's going to do that atomically. It's going to atomically compare and like put my thread to sleep. And so the way this works internally in the kernel is that there's a hash table of like all these pointers, and it stores which threads are sleeping behind this pointer. And the other thing about futexes is like there's nothing special about the state. It's just an atomic int, but it can be anything. Like you just point at 4 bytes and say compare these 4 bytes. I think they have to be forward aligned, but that's the only requirement. It can be any 4 bytes, and it'll do a comparison, and then if it's the same, then it will send you to sleep. And this is pretty magical because like there's no requirement on your state at all. And then on unlock, I exchange it for unlocked, and if the old state was sleeper, then I wake 1 on this futex. Now this is a tricky mutex because there's weird interleavings, because all these exchanges are unconditional. Like it can always happen that like some new thread comes in and like exchanges for locked unconditionally, and then the sleeper flag is cleared. Or like at the end, like you unlock at the VATS time or something. So let's go through interleavings. And this is like the model that TLA Plus does. So we're just going to do it by hand a few times. mainly to show that this is difficult and you should use TLA plus instead. But like, let's just, so we have state and we've got state prime, old state, new state. And let's say thread 1 goes to like lock it, and then it's in the critical section. Thread 2 comes along and also wants to lock, but it can't. So it's going to go to sleeper state. It's going to wait. This is the happy path. Then the first thread unlocks and calls wake. The second thread wakes up, is in the critical section. After the wait, it goes back to the loop, so it calls exchange again. And then it's going to eventually, when it leaves the critical section, call unlock, and then it's going to call one more wake because the old state was sleeper. So this is the happy path where you just like literally say like one thread has it locked and the other thread had to like go to the sleeper state and then gets woken. A less happy path would be like, what if before this wait happens here? Like what if this one unlocks before the wait actually happens? Like it just like gets right in there. Like between these two lines, the other thread does the exchange. In this case, the futex wait is going to fail because it's a compare and wait. And so the comparison will fail because the state's at unlock, it's not at sleeper. So like this wait will not actually wait. So we're going to go back and loop again. And then, yeah, so this is what saves us in this case. But then it gets more complicated once you have a third thread, because now it can come in at any other time and like mess with state. Like what if it just like, after this unlock, and like this one hasn't waited yet, it comes in and just sets it to locked, and it doesn't even know anyone's sleeping on this, because like we had unconditional unlock, and so this wake is going to evaporate because now no one is sleeping on this yet, and so what's going to save us at the end is that actually in this case it's easy, like this wait is going to fail because like the compare and wait is going to fail, like the comparison part will fail. And then, so it's going to loop around and then it's going to just acquire the mutex. And there's more interleavings. What's the last? Oh, the last one is like, what if the same thing, but this thread already went to sleep? So this wait already succeeded. And then the other threads come in and like you forget that it was ever even locked. So like this one comes in and exchanges it for locked. Like it's a new thread comes in, exchanges it for locked. The other thread unlocks at the next time, so it won't call wake, because the old state was not sleeper. So this thread's not going to wake anyone. And what saves us in this case is that like thread 3 is actually going to move on to the second loop. And that's what saves us in this case. It's going to exchange it for sleeper. And eventually it's going to like call wake because it set the bit essentially. And mainly the thing to see here is like these are, like if you do this for a while, you actually gain less and less confidence in your code because you just find like more and more weird interleavings, right? Like it just gets like you keep on coming across things that you hadn't thought about where like things get in your way. But instead you want to use TLA plus for this because it just like brute force goes through all the possible interleavings and like tells you whether your assertions hold or don't hold. Cool. I'm actually going to show how to do a futex in TLA plus or in Pascal in the imperative language. And so this is a high-level This is a high-level implementation of futexes. So if I want to verify the futexes in the kernel, I could not do this because this is too high level. But if I want to verify my mutex, then I don't want all the details of futexes in my code. I just want a high-level implementation, if that makes sense. Like you want to simplify the futex implementation to be able to like verify your mutex and have the complexity there. And so let's go through this. It's the first thing is I don't have pointers in Pascal, so I use indices instead. So I have a global map of all the futexes, where in this case there's just one because the mutex only has one futex. But like we'll get to condition variables in a second, where there's then 2 futexes, or the glibc condition variable has like 6 futexes or something involved. And so this global map is just like indexed. Pretend this is the internal hash table in the kernel, and it has there's 2 members in this struct inside of this. There's a state and there's the sleepers. The state is what we will compare against, and then the sleepers is all the threads that are currently sleeping. And so remember, the important thing is the labels. Anything between 2 labels is atomic. So since I only have one label up here and one label down here, the comparison and the adding to the sleepers is going to be atomic. It happens at one step. And this is a thing I can just do in Pascal, which is like not a thing you could otherwise do. So if the comparison fails, I leave right away, nothing to do. Otherwise, this line is not that important. I like setting local variables to 0. I will never use this variable again, but like it comes up because combinatorial explosion of states hurts you, so I like to reduce the number of states by not having local variables be weird. Pretend this doesn't exist. The important line is this line, where I just add myself, like self is like the name of the process. I add myself to the list of sleepers. This is like a set, and I just union with the set that only contains self. And then at the next label, I wait for wake. And here is a magic keyword called await. I'm going to await until not self in sleepers, until I'm not in the list anymore. And this await is just magic. ClassCal supports it. It's like a feature that's available. You could not write this in C, or the thing you want, the thing to do in C is you need to use condition variables for something like this, for await, but they were broken, so you can't. But like, this is like another feature that like the language just provides to be able to like write these kind of like higher level versions of things. Yes.
Would it be possible to like simulate await somehow if it wasn't supported, or
it?
I mean, a condition variable would do it.
Yeah, you could. I mean, you could just like keep on checking this thing and go to back, like just have like 2 states where like you check and then go to, check and go to, or something. Yeah. Yeah, you could probably simulate it somehow. But this actually like this compiles down to like literally it just like concatenates this to the like to the list of like AND statements when it falls out very nicely out of the feature set. And then when we wake, we check if the list is empty first, and if it is, there's nothing to do. If it's not empty, I say with X, and with introduces a variable. And I say X out of the list of sleepers. And what this does means it's like pick any variable. And since it's TLA plus, what I actually am doing, I'm saying branch here and try all the variables, because it will try all the possible executions. So if there's 2 sleepers in there, it will branch the execution and go down both paths with both sleepers and like try to wake either one of them, because I've got no guarantee about ordering from futexes. And then, so I take X, I take some random X out of this list, and then just like remove it from that set, like just like assign the set to itself with like, this is just a syntax for removing one item. Cool, let me see. Yes?
What happens if you don't put return? Like, is there an automatic return at the end? Or?
There is not. It is really weird. This is actually the code just breaks. I don't know. It just says like, hey, you reached like end of a function without return, and then like it breaks. And I don't know why they don't do that by default.
Okay, and then could you have put the return right before the last brace, or does it have to be inside every branch?
I could put it all the way at the bottom, but for reasons I would then have to put another label, which I didn't want to do. Like there's rules about where you can put the labels, and if I do it like this, I only need one label for the whole function. So now the whole function is atomic. Yes?
Maybe you'll get to this, but like, how do you avoid translation error?
You are very careful. I will get to that. I will get to that, yes. I will get to that, but yes, I had a translation error. You just, I don't know, debug it, and yes. Next question.
Do you understand correctly that what you did with mutex here would be, if I had a mutex that I believe works,
yes.
I would just write something like that and say, this is my mutex, and I would use it.
Sorry, this is my mutex, you mean? Or?
So you said, okay, so
yeah.
what you were trying to do here for the mutex is
yes.
you kind of said, I have a magic mutex that works, and I'm just going to use it.
Yes.
So,
yeah.
For example, if I were trying to verify my law with the algorithm and
yes.
I had the mutex, I would trust my mutex. I
yes.
would assume glibc works. And I would
yes.
write mutex that just has 2 functions, log and log, and
yes.
Everything else is.
Yes, yeah, that is, in fact, that's exactly what I did when I verified the condition variable later, like the glibc condition variable. I simplify the mutex to only be a very simple mutex, because I trust the mutex. You always want to simplify everything that you don't actually need to verify, just simplify as much as you can, because it tries all possible states, and if you have too many states, we'll get to that. It just doesn't finish, yeah. Oh, I forgot to mention this. There's also, this is how you wake all. I literally just assign like empty list of sleepers, just like empty out the whole list. And this is nice because like this is magic awake keyword. So this just works, and you don't have to notify anyone. It's nice that the language works like this, and you can just write this thing. Yes?
So if I understand correctly, this is kind of still describing how a mutex works. It's just a very simple feature. view text.
Yes.
Is there a way to declaratively describe what a view text is without saying how it works at all? To say these are the properties of a view text and this exists.
I don't think so. I'm not sure.
I think I might say that this is closer to what he wants, but actually, this isn't about how the view text works. This is describing what it means for the view text to work.
Yes. Yeah. You want this to have enough detail that your code breaks if you use the view text incorrectly. Like if you had a bug because you're using view texts wrong, like this has to have enough detail that your code will break, and I think it does. But like no more detail than that. Yes.
Do you actually have to write it, or is it like a library of common primitives like view text, mu text, or whatever?
So I think there is libraries, but I actually am not an expert, and I only ever use the basic features. So I wrote things myself. But yes, there is a way to like import libraries, and I never use it, so I do not know. Okay, so let's get to condition variables. So the way to think of condition variables is like, I like to think of them as a generalized view text. And so instead of compare and wait, the operation is like check arbitrary condition and wait. So like in our example earlier, it was like check that the list is not empty and wait. But you have to do that atomically, right? You have to atomically check the list is not empty. And if it is, if the list is empty, go to sleep is what I want. So like the opposite of what I said. But like and that has to happen atomically. Like atomically check if the list is empty and go to sleep. And since it's arbitrary conditions, you can't do this. So it always gets used together with the mutex. And there's a protocol you have to follow for condition variables and mutexes, how to use them together. So here's the condition variable implementation, which this is once again good code. Feel free to use this. Like this is fine. In fact, this is like we said earlier, like when pthread condition variables broke, like I switched our code to use this instead, and this is fine. So the main entry point is this wait function where you pass the lock, which you have to hold when you enter the function, and you pass an arbitrary predicate, which in this case is like the list has to be not empty. And so we say like while the predicate's not true, so while the list is empty, call the other wait function. The other wait function loads the state, which is our view text, it's just some atomic int, unlocks and then goes to sleep if the state is still the same. And this is just to make the interleavings work. So when we go to sleep, we don't hold the lock anymore. After we get woken up, we reacquire the lock, we check the predicate again, and if it is still empty, then we go back to sleep. If it's not empty, we leave the function. And so this is like check arbitrary condition and wait. And then the notify, the way it works is you have to make the predicate true on the outside of the function. So you have to put an item in the list outside. You have to do that while holding the lock, and then you have to unlock and then call notify. So there's no lock involved here, but on the outside you have to follow the right protocol. You have to like inside the lock make the thing true and then notify. And so what this does is just like all we have to do is we have to just like make some change. We have to perturb the state in some way so it's different from before, so that this thing doesn't accidentally go to sleep if something changed. In this case, I just add 1, and then I call wake 1. Yes.
Is this technically incorrect if you manage to cycle all the way through and wrap?
If you manage to wake 4 billion times in the time, if you manage to wake 4 billion times between these two lines, so you need an interleaving of threads where like between this line and this line, some other thread has woken 4 billion times. Then this would break, yes. Which I think never happens, so I claim this is correct. But yes, it could. Well, no, the schedule is not that bad. It just doesn't happen. Because there's nothing blocking you between these two lines. Yes.
I'm a bit confused. So you said we hold the lock,
yes.
We do the modification, add to the list,
yes.
We unlock and then call notify 1.
Yes.
The then bothers me because when we unlocked, like somebody could have taken that element from us, so we cannot
yes.
call the notify.
That's fine because we like the other function will recheck the predicate after it gets woken.
Yeah.
Ah, okay.
Condition variables are allowed to give false wakes.
Yes. Yeah. Yeah. False wakes are allowed. Yes. And sorry, notify all is also exactly the same. The only difference is instead of waking 1, I wake int max. Cool. And then this is actually all I want to talk about here. I'm also going to show one other thing, which is the thing that actually broke with condition variables, which is the It's the OCaml master log. So OCaml used to be single-threaded, or it had multiple threads, but like Python, it had like this master log where all the threads have to agree which one can run right now. And it is actually just a mutex that has a count inside of it. And so they built their own mutex using a mutex and a condition variable. Okay, so the internal mutex is only used for like coordinating these functions. So you take it at the beginning of the function and you like unlock at the end of the function. And same down here, you lock and unlock. And this is like very idiomatic way of using condition variables. Like it follows the protocol exactly. So like you say, I take the lock, I check if the master lock is busy. If yes, I increment waiters and then I go to sleep. This waiter count gets used like in some other place to like check that if nobody's waiting, I don't have to like give up the master lock, but it's not checked here. And then when I wake up, I decrement the waiters. I set busy to 1. If not, some other thread came in between, and then I call unlock. And then when I release the master lock, I just like set busy to 0 inside the lock. After I'm done with the lock, I call signal. So this is exactly how you use condition variables. Like this is very like idiomatic. And you might say like these can just be atomics because I'm just incrementing, decrementing, like the count. And this busy can also just be an atomic variable, and then I wouldn't need the mutex. But like one thing I forgot to mention is like these are all relaxed atomics. The condition variable itself does not give you any sequencing. The sequencing comes from the lock. Like the mutex actually gives you like that, like the acquire release semantics. And so, well, that's one detail. But also like if you tried making all these atomic and then didn't have the lock, also the interleavings just wouldn't work out. And like the best way to find out why it breaks is to put it in TLA plus and like see which interleaving breaks. And it's actually kind of fun in that like if this wasn't atomic, you would be allowed to move this line 1 line up, but so it's outside of the lock, but you still have to lock unlock and then call notify. It is very strange, but you have to follow exactly the right protocol. Otherwise interleavings don't work out. But this is code that broke. This is very idiomatic, which is like it's a big problem that this code broke because this is such a straightforward code for using condition variables, and this will just deadlock forever with glibc condition variables. Cool. Any questions? Yes.
Wait, so sorry, the goal of that code was to be able to keep track of how many like.
Yes. Yeah. I think the only reason why they have this is like they wanted a mutex that has a count inside of it. So they built it on top of mutexes and condition variables. And like they have a yield function, and the yield function first checks is the waiter 0, and then in that case it doesn't do anything. But I'm not showing that here. Yeah.
Do you know if they could have done it with like a try lock and then increment the counter atomically or something like that?
I don't know. It's.
But this is easier. This is definitely easier.
Yes. Yeah.
Why is it safe? So con signal, pthread con signal.
Yes.
There's no way that can get reordered. Like you mentioned that it's relaxed. So why don't we need that inside the lock?
I don't think it'll get reordered. I used to not. Yeah.
So the unlock synchronizes with the wait.
Yeah, I mean.
It doesn't help to do the signal inside the lock because nobody else can make forward progress while you're holding the lock.
Right.
So all pthread con signal is doing is saying, okay, other threads, they can have their chance to wake up now. If something else comes in between and makes the condition wrong, they still wake up and they check the condition because they're allowed false wakes.
Yes. Yeah, and like another way of thinking is like if you can't, like it's not incorrect to signal inside the lock, but like the thing that's awkward about it is you wake someone, and the first thing that they want to do is they want to reacquire the outside lock. And so if you are still holding the lock, then they just go straight back to sleep until you release the lock. So that's like, yeah, you just want to signal outside the lock. But the details of like this interleaving, I forget. I've definitely walked through this a few times, but I don't remember. All right, let's look at glibc condition variables. And so it doesn't fit on one slide. In fact, it is quite big. So I'm going to scroll through it mainly to see how complicated this thing is. So here's the broadcast code, and like there's lots of comments and lots of like details. This is like the group switching code because there's, I will explain in a minute, there's 2 groups and there's lots of comments and lots of atomic operations and details. Then we're gonna go to this, the condition variable has inside of it its own mutex, its own implementation of a mutex, because different signalers have to coordinate among each other. This is also a more complicated mutex than what I'm used to. And so this is the acquire release of the internal mutex. There's some other tracking here that's going on. There's the signal function. Here's the actual struct, which is, I think, 48 bytes of state. And I think there's, either there's 5 futexes in here or 7. The things you can't see which ones are futexes because they're all just unsigned ints. But like, I think it might have been 7 futexes in here, if I remember correctly.
I almost have to believe it because there were weird bugs that nobody could find.
Yes, yes. No, you look at this code, you're like, yeah, this is, yeah. And this is the big one, this is the wait function. But this is also where the bug is. And it's just lots of like details, lots of comments. It is, I don't know, like, yeah, this is actually the buggy, this is where the bug is. This is like we consume the signal, but we might have consumed from a later group. And so, yeah, this is like the bug and then, cool. I will actually, in this talk, never fully explain these condition variables because I cannot. But when preparing this talk, I like was reading through this code again, and every time I get hopelessly confused. In fact, actually, wait, don't I have a slide on that? This one. Oh no, oh no. I got into the wrong state. Thank you, thank you. Okay. I'm actually going to first explain the old design, which had the bug, which just going to walk through it once and explain why they have this complexity now. So this was like the way they have like the wake-ups and walk-in, and this had the bug where like a later thread can come in and like steal the signal. And so when you wake, you increment the left counter, and when you get walk-in, you increment the right counter. And if they're the same counters, then that means no signals are available. And so what would happen is like another thread comes along and goes to sleep, and then we signal. And then if like this thread wants to like wait again, it will just say, hey, a signal is available. I'm just going to increment this counter and take the signal and leave right away. And like it won't actually go to sleep. And then this guy will go back to sleep and like, because no signal is available. So this was the old bug that they didn't like, it wasn't strictly a bug, but they didn't like this behavior, and this is where the complexity comes from. And so the new design is that there's 2 groups of sleepers. And so wakers always are going to wake in group 1, and sleepers are always going to go into group 2. So you always take things out of this bucket and you put things into this bucket. And when this bucket's entirely empty, you switch to 2 buckets. So you never, so you can never wake a new sleeper because they always go to sleep in the other bucket. And so you need like 1 futex per group, and you need a count to know when the groups are empty. And so you only ever increment the count in group 2 when you go to sleep, and like and then you make a copy on group switch and you decrement when you wake them. And then there's some complexity where like for some reason waiters also decrement the count. I will not take questions until the end of the slide because yes. And also group switching waits for this for some reason, but only if things are actually sleeping. There's also a fast path when you're not sleeping. And there's actually another complication where we don't actually group switch as soon as the group is empty. We group switch on the next signal after the empty group. So like we take everything out, it's empty now. The next signal finds an empty group, and then it says, oh, I have to switch to 2 groups. That is a problem because if you now have an empty condition variable where no one's sleeping, you're constantly switching groups, which is actually expensive. So there's also a total count of the number of sleepers, which we have to keep in sync with everything else. And then this is getting complicated, so that's why there's the internal mutex. And this fast path leads to ABA problems, so we have the sequence number to keep track of when the group started. And basically, I gave up. I cannot understand the condition variable. I've tried hard, and every time I follow for a while, I read the code and I get this makes sense and this makes sense, and then oh right, I had to keep track of this state. I forgot that we also have to keep this thing in sync, and eventually I fall apart and I cannot understand what's going on. Yes.
Why did they have to like reinvent condition variables? Because they're implemented in so many places so many times. Why did they have to come up with a new convoluted implementation? Do you know?
Like a licensing thing, maybe?
I don't know. I actually don't. I mean, I think they just had like. I've read the commit message of like that created this condition variable, and I think it just says like here's a new condition variable implementation that has like it fixes this like problem with like the late sleeper coming in. I don't know the conversation that led up to that. I don't know. I never sought it out. I don't know.
I assume it's some combination of performance and fairness.
Yeah.
Well, and history, because, you know, yes, condition variables have been implemented a lot of times, but possibly one of the earliest, well, widely available implementations was in this library.
Yeah. Anyways, yeah, so this was too confusing and I was just like unable to follow this. So this is where we get to TLA plus. And so the way you translate this to TLA plus is actually, the most important thing is always simplify. So like I cross out lines where I don't know, like where I don't need to simulate them. So this is some glibc like tracking thing, I don't know. I get rid of it. I remove the timing stuff because the OCaml master log doesn't use timing. It just always waits infinitely. It doesn't have a timeout there. I don't do any error handling, and then the only line I actually have to translate here is like this line at the bottom. And so like, this is what my code looks like in PlusCal. I have like CV wait, I declare my local variables, and then I call like this fetch add at the bottom, and that just matches. The other thing to point out here is this takes no arguments because there's only one condition variable involved. So I just made it all global, and so I can cross out these up here as well. And then here's another function that I translated, and like just showing the mapping that like this is all like pretty straightforward translation, except you have to do some work. Like this fetch add is like one thing, for example, is like this in C, this returns the old value. I could have done that here too, but I just compare against the new value. So I compare against 1, so I compare against 3. Small differences like this show up, you just have to be careful. This fetch and I like wrote a helper function called clearbit because it doesn't exist. But yeah, I actually have, I've annotated that very big function, this wait comment, like the biggest function in there. And I have on the left side the C code, the actual C code, and on the right side I have the PlusCal code. And I've color coded which things belong to each other. And I'm just going to scroll through this to like show that it's like the same code. So like here we fetch add 2, and here's I add 2. One choice I made is I put these two into the same atomic block. So like there's no label between these two lines, because I reason that these are just local variables, so like interleavings don't matter. In general, I try to be pretty careful about like having a label each time that actually like interleavings might matter. I will talk about it in a second. I had to reduce number of states because otherwise this would run for too long. But yeah, here's a fetch add of 8, fetch add of 8. I don't need the return value. Also, in here I always have to like modify inside my fewtexes map because that's how I decided to implement fewtexes. Then I don't need this private flag because this is related to like inter-process condition variables, which this is not. Unlock the outer mutex. Don't do any error handling. This is not translated. Then I read atomic variable. I have my double loop. Let's see. And this is just, let me see. These match 1-to-1. I didn't do the spinning because TLA plus already will try all possible interleavings. So when I get to the spin wait, it will already try what if I wait 0 times, what if I wait once, what if I wait twice, what if I wait all possible values of waiting. So I didn't have to like do the spin waiting because it already does that. &1 gets translated to mod 2 equals 1, why not? Yeah, these like, this is complicated. Oh, I didn't do memory ordering, and I'll have a slide on that. But like, yeah, I didn't think the bug was in like whether you have to use like acquire or release or something. I didn't do that. Otherwise, here's where we actually finally go to sleep. Call fewtex wait. This has like some cancellation logic where you, in pthreads you can like cancel a thread. I didn't do any of that, so just like don't translate this code. All this error handling is not there. We always go down the else branch. So we call deck grefs. Wait, not this one, deck grefs. This is the important compare exchange where we like decrement the signal counter. There's no compare exchange in TLA Plus or in PlusCal, so I had to like implement it. So I do the comparison. There's only one label, I do the comparison. On success, I do the exchange. On failure, I do the I assign back to the local variable. That's what compare exchange does. I just had to do the translation. It's all. This is where the bug happens, where we took the signal possibly from the wrong group, and yeah, I'm not going to go into any of this too much. This compare exchange once again blew up into multiple lines. The main point is it's a one-to-one translation. I literally just went through line by line. I might have even started by copying these lines, I think, and just like then translating one thing at a time. And when I'm done, finally, I am at this confirm wake up, which I inlined. So like these lines map to these lines. And nope, I don't know. Cool. That is this. Any questions on this part? Okay. So that's this. This is the same as the slide. I don't do the spinning. Yeah, what about memory order? I have not actually done this, but I'm pretty sure you can do memory order in TLA Plus, but you have to simulate it. So you literally have to have like another process. Like you can have different kinds of processes interacting, and you would have to like put all of your like writes into a queue, and then some process is responsible for just popping from that queue. And if you have like a release write, like an atomic release, then it has to like wait for all the previous things to be popped before it is allowed to be popped. I didn't think I needed it, so I didn't try to simulate this. But you would actually have to simulate like memory order. Yes.
Did you try running the original code with like sequentially consistent everywhere and then see if it still reproduces? Because that would quickly show up as the problem.
That is a good idea. I should have done that. I mean, well, so the original bug description was really good, and they already had a really good theory for like what caused the bug. And so I didn't think it was memory ordering based on that. So yeah. Okay. And then yeah, this almost just worked. I had one bug where like it errored out on something that couldn't possibly error out, and I double, triple checked, and that answers the question for how do you avoid translation errors. You double, triple check. It's not fun work, but you do it. And the big thing you run into is like exponential explosion in states. So like the first run of this just never finished, because it tries all interleavings every time there's a new label. It will try running all the other threads through all possible states while you're waiting at this label. And then for the next label, it does it again. So you just like blow up exponentially. But like it still didn't take much to get around that, because like the biggest speed up was the temporal checks are slow. So I remember I had like that check where like saying, if this is true, then squiggly arrow at some point later in the future. Some other thing has to be true. They're slow, but there's a built-in deadlock check that is really fast, because all it has to do for that is just like walk down the tree until it finds a state that cannot progress. So it's already like built into the tree exploration, and like that was actually enough for this case. Then I simplified. And so like I replaced the mutexes with very simple mutex implementation, like you suggested. And then these are just like the most rewarding optimizations ever, because you get exponential speed ups. So it goes from like taking forever to finishing overnight to finishing in 20 minutes. And this is just very fun to do. The other thing I did is I limit the depth of how far I explore. So the actual test that I verified works with the patch is I call lock, unlock on the OCaml master log 3 times in 3 threads. That's as deep as I can go. If I go any deeper, then it just like never finishes. Yeah, this like, and then if you want to be sure that it works on deeper things, you just have to like use your own reasoning. But like, this is what was required to like make it break even with the mitigation patch. Cool, thanks. And so one thing is like, you might think this is a lot of work to do up front, where you have to like do all this translation, which takes like a day, and you have to like run your test overnight and it doesn't finish, and then you have to optimize, and like you have to do all of that before you even get any results at all. And so like I went into this with a lot of confidence, because I had used TLA Plus before for my own condition variables and like found it very impressive. But there's other reasons to be confident here, and that's like if you look at the literature on multi-threaded bugs, they consistently always find the same things, which is that like these bugs are really simple if you can control the interleavings. And so they say like 96% of concurrency bugs happen with just 2 threads if you can control the interleaving. In my case, I needed 3 threads, so I'm in the 4%, but like you never need more than that. It just doesn't happen. Or 97% of deadlock bugs is just like 2 resources, which makes total sense. Almost 92% of bugs, just like you control 4 memory accesses and you have the bug reproduced. And like TLA Plus essentially is like the engine that does this. It like explores all the interleavings and it controls, it does like this like controlling of the interleavings. Yes, question?
So does this actually mean that if you write like a normal test for multi-threaded whatever, going beyond 4 threads is completely unreasonable? When you try to hammer or something.
Well,
Might depend
yes.
on your schedule or how many cores.
Yes, I like often you need to actually run like more threads than you have like hardware threads just to like get weird interleavings. Because like if the threads never get interrupted, you don't get like in this case, to get the bug, you have to like stop at one specific line for a long time. And if you don't have enough threads to like saturate your scheduler, then like it will never cause to stop there for a long time. So
so it's a scheduler.
yeah, you have to like overwhelm, like for many bugs to reproduce them, you have to like overwhelm the scheduler essentially. Yeah. Another comment on this, I found this personally true to be in other areas as well. I used to work in video games, and when I would write tests for my AI characters, it's the same reasoning. Like you can reproduce all the bugs with just 2 or 3 characters. It's just like a thing that's true in general. Yes?
I don't recall if you addressed this, but how do you figure out how to optimize your TLA plus or your code in there? Like,
Yes.
How do you figure out where the bottleneck is when it doesn't finish simulation?
How did I do that? I mean,
Is there a breakpoint you can put? See, it's like,
you can. I don't remember if I did anything there. You can probably write like something where you cause it to like break after a certain time or something, like write some custom assertion. I don't think I did that. I think I just like basically every state you remove will massively like decrease the exploration size because it always tries all the interleavings, and any new state is like, so you just remove, like removing a few labels will already lead to a massive speed up. And
like which ones to remove? You just guess, I guess.
yeah, and I mean, so in my case, it really didn't take much. So like maybe if I had like done the obvious things and then like still didn't have success, maybe then I would have had to get more serious. But like, I never had to like really get serious about simplifying. Like I stayed very close to the original code, basically. Yeah. Okay. Let's look at the trace in TLA plus. This guy. So this is the actual code. There is this is like the translation of the glibc code. I'm just going to show the OCaml master log because it's like easier to read. Where is it? It must be after all of this. Yeah, you just do the code. Here's the master log, which is like exactly the same code we saw before, which is like log mutex, while busy, waiters +1, call cv wait, waiters -1, busy equals true unlock, and like the same for here. This yield I didn't actually end up using, but this is where like the shortcut is for like with waiters equals 0. And then here's my main loop, which is very similar to the spin log. So I have my maximum loops, which is like one of the constants I declared on top of the file. I just say while num loops greater than 0, and then I will explain this again. There's another magic statement, which is very useful. But basically in a loop, I say acquire master log and then release master log, and then I'm done. I do that 3 times because maximum loop is 3. This either is it's another magic keyword where I can say to TLA plus, at this point, please branch your execution and try both paths. And so I say like either do this or leave the loop. Like this just says like go straight to the end and like you're done. Like this is where it ends. And so this is useful to get a shorter trace out because if it reproduces the bug after one thread has like called log unlock 3 times and the other threads have called it maybe twice, I want the other threads to just get out and like get to the end because then I have my deadlock. This will make more sense in a second after I show the actual trace. So here's like my actual run. Down here, like these I didn't actually check anything. Here's my globals that I defined, like max num loops is 3. My procs is P0, P1, P2. These are like my own globals where like I just define them and then like I use spin locks instead of for the mutexes, I set them to true. This run took 24 minutes. If I run this with the mitigation patch, it takes like 2.5 hours, I think, to get to the broken case. But that's like, it's totally fine. Like, and on the right, I get like deadlock reached, and here's the shortest interleaving that like leads to the, you get all the states, and you can click on it, and like the first click takes you to TLA plus, the second click takes you to pluscal, or control click takes you to pluscal. So I see like, I don't know, we're in start, one of the threads calls acquire master lock, and then calls, it's just some sequence of state changes that like these go through in order. And all the way at the bottom, if I go all the way down, I'm in my deadlock state, and I can look at the program counter, and I see like P0 is done, P1 is done, and P2 is in wait for wake. And that means I've like reached the deadlock because now no thread can advance. Yes?
So this is good for proving there is a bug, but it can't prove that it's correct? Like there is no interleaving where it would be buggy, or how do you?
Well, so when you fix the bug, you run this, and it takes 4 hours instead of 2 hours, and it never finds a deadlock.
So you still don't know. It could be that after 8 hours it would have found something?
No, it tries all the states. For the lock unlock 3 times, it explores every single state.
Oh, okay.
Yes. But I only lock unlock 3 times, so I only have confidence up to that point. Beyond that point, you have to use your own custom reasoning, or your own like brain, basically. Yeah, this interface on the right where you see all the state just dumped, I actually didn't find that useful. So what I did instead is I have this giant spreadsheet where I copied out all the values, and I annotated like, let's see, on the right I have like some variables that I thought were important. I copied them out and like have them in here. On the left, I color coded which thread's actually active at any time, and then like I did this all manually. Like I highlighted like these lines are the important lines, like, and I found this much easier to work with than like the other interface. And this is where the actual bug happens, and like, yeah. So just to show that like, I think like the interface inside the TLA toolbox is useful for like simpler things. Like when I verified my own condition variables, I never had to like do anything like this. But for glibc condition variables, it was not enough. I needed to like make my own like interface to like see what actually happens in parallel. And I stared at this for very long times, and like you can see also the shortest interleaving is 325 states. So like it's like this is with the mitigation patch. So this is the more complicated thing that takes 2 hours to run. But yeah, it's this is not fun, but it's kind of, I don't know, maybe it's a little fun to like try to like figure out where the heck does it go wrong. Yes.
So I'm trying to imagine if you took the actual C code and then instrumented it so that at the places where it sleeps, you could control when threads wake up.
Yes.
And then try to write your own, state space exploration of that. I don't know how easy that is.
Yes.
Do you think that would have found it in a reasonable amount of time, or are there a lot of optimizations here that would just be impractical to try to implement?
So one other thing about the bug report is very early on, people identified where you have to put a sleep. So some person posted on the bug, in the bug report and said like, if you put a sleep before this line, you get the bug very quickly. And it is exactly the right line. Like I can say that now. It's still, I don't know, it's still like harder to reason from that than like when you actually see like, okay, what happens after that and what happens before that? Maybe if you had like reversible debugger or something, but I don't even know how that interacts with the threading thing. So yeah. Cool. Not this one, this one. That's the same thing. Yeah, so the actual bug is like, this was already in the initial bug report, they had it pretty much right. It's like, the condition variable will think that in one of the groups there's like 3 threads sleeping, but there's actually only 2. These numbers are not important, it could be like 0 and 1. Like it will think there's 1 thread sleeping, but actually there's only 0. And so like, and what that means is like the next 3 signals will not cause a group switch. And so one of those 3 signals will not wake anyone. And like in code, there's like this block, which I shortened the comments heavily to fit it on the slide, but like there's a comment here that's like saying, oh, well, at worst case, will cause like a spurious wake up, which is like not actually the worst case. So
Well, there was a dot, dot, dot there.
No, the dot, dot, dot is because I shortened the comment by a lot.
Oh.
The actual comment is like this huge, like I couldn't fit it on one slide otherwise. And so I'm going to go through the interleaving that actually causes the issue. First, I'm going to go through the happy path to give you a feeling for how this condition variable behaves, and then we'll go through the buggy path. So this is all in the context of the OCaml master lock. So someone has to hold the lock. If no one's holding the lock, the condition variable does not even get involved, right? Because they can exchange it happily. So someone's holding the lock, and this other thread wants to like get the lock, so it has to wait. At some point, this one gives up the lock, it signals, but the new waiter always goes to sleep in the other group. So like it finds, oh, I'm signaling on an empty group, I have to first switch, and then when I switch the group, it does the math to say like the new group is of size 1 because it subtracts these two numbers, and then it will signal after that. It will immediately decrement the number again and add a signal. The signal's on the same side as the other one went to sleep. So now this one gets woken and like decrements the two numbers, and there's lots of internal accounting, like always decrementing, adding multiple numbers. I didn't even show all of them. So that's the happy path, and then at some point later, like some more exchanges happen. Thread 1 holds the lock again. Now 2 of them want to sleep. Still the happy path actually. So now it signals. It again has to switch group because its group is empty. So it switches G2. It knows the size because it can subtract these two numbers, and it then immediately wakes one of them. So now the size is 1. There's a signal available. One of them takes the signal, and deck giraffes deck the signal. So this is the happy path of like how this is supposed to work. There's lots of group switching going on, which is one of the things I want to show you. And the bad path is if we go back to this, like after this deck signals, there's this like secret step that I didn't show here, where it next checks whether it stole a signal from a later group. So like it might have accidentally like been not scheduled for a while, and group switching happened a few times, and then this decrement of signals would have been in the wrong group. Because it would have been in a future group. It would have like decremented some future group from 1 to 0, which would have then like stolen a signal from somebody else. And they have this because there's this fast path in there, and like it's complicated. But so let's say now it's still after this line, and for a long time like other threads do exchanges and like use this condition variable, and we're in a future state where like the group has actually switched twice, and now this one actually runs its check and says, oops, I stole a signal from a later group. It didn't, it like everything was correct, but it took long enough to do the check that it thinks it stole a signal, even though it didn't. And so it will just add one signal, just in case. If it actually had stolen, this would be correct, but it didn't, so this is actually the wrong thing, and this is where the bug comes from. And then some more time passes, group switching happens until this is like the active group again, where we wake things. And I'm kind of magicking together a state here where thread 3 is about to go to sleep. It's already incremented the sequence counter, and so the group size is already 1, and this one's about to wake one thread in this group. The group size is 1 because thread 3 is about to go to sleep. It hasn't incremented giraffes because it's on the fast path. It's complicated, but it finds this leftover signal from earlier and says, I can just like right away leave because there's a signal available. And so it just decrements the signal and doesn't go to sleep. But the group size stays at 1. So these are the same two last states. I just needed more space. And then, so it gets woken up, but since the master lock is still taken by some other thread, it immediately goes back to sleep because it's still busy, but it goes to sleep in the other group. Now, at some point, the lock's given up. This thread signals, and it's going to decrement the group size, it's going to add a signal, but the signal's on the right-hand side and the sleeper's on the left-hand side. And so the signal was on the different group than where the thread actually went to sleep. And like, now at this point, we're deadlocked forever, and like we're just hopelessly like, stuck in this interleaving. And I felt like I had to go through this once because you have to at least like see the interleaving of what the bug is. And I know this doesn't give you much, but it felt like I had to go through it. Cool. Let's go through the patch. So here's the history again. It's like bug reported, and I submit a fix that actually fixes the bug, but somehow 5 years passed, so what happens? The first thing is that there's lots of discussion where we're all slightly wrong, and like, because also I think the mitigation patch fixes it, but like they don't want to take that, they don't want to take my patch because of performance considerations, and like I get a bit burnt out eventually. I stop working on this. Next year, this other guy comes along called Frank Barris, and he shows a very good understanding and posts another patch. He clearly knows what he's talking about. But then that also fizzles out. I actually don't know what happens to that. I reread the comments just before this talk, and it fizzles out somehow. I don't know. So a year later, my work runs into this, and because we finally upgrade to OS version that uses like this 2017 glibc or later, we have the mitigation patch, but still our programs just randomly freeze sometimes. And so I get some work time to work on this. I post like a better version of my old patch. I post a new patch that's very nice. But it like radically redesigns the condition variables to be like just always incrementing, kind of like the one I showed earlier, except with 2 groups. But they asked me about Frank Barris's patch, what I think about that guy. And the thing is, at this point, there's 3 patches. There's my first patch that I don't like for performance reasons. My second patch, which is like a big redesign, which is actually very nice, but it's a big change. And then Frank Barris's patch has a nice property of being a very incremental change that also actually speeds up the condition variables. And I stopped working on this again for a while because we no longer have the problem because we switch condition variables. But eventually I think this is ridiculous, and I finally like spent some time to make this really nice and like make a very nice patch to like fix the thing. So his patch has the idea of making the ABA problem go away by like always making signals relative to the group start. So if the group starts at 4, like the signal's at 6, that means there's 2 available. You never decrement below the group start. And if you wake up and if you accidentally try to do the compare exchange, it will never succeed because the number just doesn't go back down to where it used to be. And I like this patch in theory, but I'm confused by some of the code. It's the same as the original condition variable code where I'm like, I follow, and then I'm like, why does this happen? Like it causes like another wake here, and I don't understand why it caused another wake here. So what do? I use TLA plus again for like this code. And I find that like every single time where I'm confused by like his patch, it turns out the code was just not necessary. And so, this part. So like when there's double checking, I just like, what happens if you only check once? And yeah, let's just go through, look at the code. It's on that screen. Actually, I'm gonna show, one thing I have like here in TLA Plus, I have like my sequence of like verification things where like I have with his patch and then like where I like remove one thing at a time. And so the patches are like, here's my sequence, I submit it, we're literally gonna look at it. The first patch is just like Frank Barris's patch. This is a good patch. It like fixes the issue and at the same time removes lots of code and like simplifies condition variables. The second patch is just like, after that, fix up the comments and like fix the indentation. So if they just want his patch, they can take the first 2 patches from my sequence and they will have a good state and they will be happy. And then the third one is like, I like verify in TLA Plus that this wake is unnecessary. And so I fix the comment and I remove the code. And like, it is nice to be able to like verify this and like simplify the code and like be certain this just never happens. I mean, I reasoned about it first and then I like was like this, I can't understand this part. And then I was like, oh, let me just verify it. It's actually not necessary. I have another patch where we were quadruple checking something and I just like remove it down to 1 check. So that is this. And then there's a sequence of like patches where I remove a variable and like clean up some things and like, I don't know, do small things in the last patch, like uses all the bits of these fields because we no longer need various flags that were in there. And just, yeah. I post these patches and I figure they cannot say no to these anymore. And in fact, they do not. So finally, like these patches I post them in 2023 and they're finally in as of the beginning of this year. And I don't know what happened in the time. I just had to keep on like poking, saying like, hey, how about those patches? And like, when are they going to be in? And they're in now. So that's it. How do you get started? I recommend this video course from Leslie Lamport. I claim you can be productive in less than a day if you follow this course. I still only know the basics of TLA Plus, and I did all of this, and I just did the course and then went on to do all this stuff. It gives you superpowers whenever you do like distributed work, because it just like checks all the interleavings. And here's what I learned. And that's all I have. Yes.
So the code looks awfully complicated.
Yes.
A lot of the time I don't do a lot of programming, but all the time I see code like this. You usually can find some abstractions or some ideas that make it simpler. Do you think this code is rewritable in the ways that it does the same things, but it's like much easier to understand? Or is it just inherited complexity? What's the problem is?
The complexity comes from, so my first patch I submitted, like the complexity comes from having a fast path, both for the waiter and for the signaler. And so there's like they do like various accounting things where they have to keep things in sync. And like my first patch like simplified things by a lot, just like by saying there's no fast path, or like in group switching, we always wait for threads to leave before we switch the group. And that just simplifies things so much because like I get rid of like, there's still a fast path, but we have to wait for that one too. But like, yeah, the complexity comes from, it comes from wanting to have these fast paths in there. And so simplification is like, don't have those, but then, I don't know, like you would get complaints about potential performance things. I mean, but yeah, fundamentally, so the other answer is I don't fully understand this code. Like, so I cannot simplify it like that much. Yes, yeah, yes.
Do you have any sense for how much faster the fast path is versus like naive implementation?
So the fast path is that if there is a signal already, or we first check a few times if there's a signal available already, and if yes, we don't even go to sleep. That's the fast path, which is a totally reasonable thing to write. And the other fast path is like we don't wait. Like those threads that didn't even go to sleep, we don't wait for those on group switching. That's the other fast path. I think those two are meaningful improvements. I think that I would like, I understand why they have it. Like I don't think that those are like, yeah, I think those help a lot. Yes.
Did you find translating it to TLA help give you any more intuition about how the algorithm actually worked, or did it just make you more confused?
No, it definitely helps. It's like, I mean, yeah, it's always a thing where like if you rewrite a piece of code, you understand it afterwards. And it did not happen immediately. It required banging my head against it for a long time. But I understood many of the concepts afterwards. I never, like, sorry. When I say I don't understand the code, I still don't understand all the interleavings and all the details. But like at the high level, I can definitely understand like everything in there now. And like that came from working on it. And like, yes, the translation definitely helps. Yes.
Usually, no bug goes without a test. So can you unit test now that you understand what the fix was? Can you write a unit test for this?
So the maintainer of this wanted to add a test where he would inspect the internal state. I mean, really the test is like, you should take this TLA plus code and submit it to glibc, and then like next time someone wants to make a change, they have to like make the change in both C and TLA plus. And then like, in my mind that's the way to test this, because like I don't know how to get the tricky interleavings in a C test or in a C++ test. Like I know how to test the simple cases. I don't know how to like cause weird interleavings that I never even thought of to happen in like a unit test.
What if you hook into, like I saw some codes that has templated atomics where you replace atomic with I don't know something. What if you hook into atomics and muted sys and things like that?
Yeah, in a different context, I once tried doing something like that, where there's like this algorithm called like block exit or something, which like you can annotate your blocks in C++, and it will cause all possible interleavings just in C++. I would have to find the paper again. I've implemented the algorithm. It's actually very, very practical and it's good. It's actually much slower than TLA+ because it's not like C++ is not built for like trying all the interleavings. But yeah, something like that does exist. But I mean, really the answer is like use this.
Yeah.
Yeah.
If you were willing to go to the trouble of like, undermine all of your locks and atomics and so forth, and turn everything into coroutines, and then
Yes.
you could write a unit test that, that says do exactly this interleaving and
Yes.
see if it works. But
Yeah.
Couldn't you also do it via
Would be
state
a lot more.
injection with the correct internals?
We are what injection?
State injection, so you just like set up, like
Yeah.
I'm at the state that I want with like an internal function, and then test that internal function instead. It's not as
Yeah.
elegant necessarily.
And then the next time you change the state at all, you have to completely rewrite the test.
Yeah, I mean, yeah, you can at least,
You write the code implementation every time you change it.
yeah. Yeah, I mean, yeah, that's actually what happens. Like you rewrite the implementation every time it changes. Yeah, you can at least make sure the same bug doesn't happen the same way, right? Like, which I actually like having tests like that. Like I'm always a fan of having like, at least make sure the last thing doesn't happen again, because the same thing can trigger multiple ways. Like the thing is also like the C code is not amenable to any of these things. Like you pretty much have to make a copy of it anyways to even like be able to like inject your own things in there. So once you make that copy, just use TLA plus. I don't know.
One option could be using sched_x. It's like a Linux thing that was added recently, and you can basically hook in your own custom scheduler, and you can choose whatever delays or interleavings or whatever you want by telling Linux how to schedule bits.
That sounds good. Yes. That sounds very relevant. Because yeah, I mean, it still is like a thing where. So it took 2 hours in TLA plus to reproduce, like with the mitigation patch, and if you cannot try all the interleave, like okay, no, sorry. I guess the question is like after the fact you can reproduce the issue if you control the scheduler and you have like the threads, then you can at least reproduce the same issue, yes, and then verify that does not happen. But you would not have been able to like find the issue because it would have just like taken forever. Like you would have not. Instead of 2 hours, it would have taken you like 2 months.
What the test is supposed to do, just make sure at least that particular bug never
Yes.
shows again, as opposed to any bug never shows up.
Yes. Yeah. I mean, yeah, I'm always a fan of having tests like that. I'm not going to say no. It all sounds like a lot of work. Yeah. Yes.
So like how many years did it take from the initial report to it being fixed?
5 years. Yeah.
Pretty fast glibc.
You said 2017, no?
That was not the report.
Introduced.
Yeah.
Ah, well, so the bug came in then.
Yes. Yeah. I mean, I later went back and like there was people talking about the bug in 2019, but they didn't post it to the glibc bug tracker. Like the bug was posted on glibc bug tracker in 2020.
Was that figured out empirically for 2017 by just trying to run the test and see when it started working again, or?
No, I just looked
at
at
how the actual bug is really showing up.
No, I just looked at the history of the source code. So when they switched to this implementation, so there's exactly 2 implementations of condition variables in the history of glibc. There's one big commit in 2003 and a second big commit in 2017. And you only have to look at those 2 commits. That's like nothing changed after 2017. It was the same code until now, until 2025.
But no, what I'm saying is, can you spot the code that made the?
Yes, yeah. It was a big change in 2017 when they rewrote it entirely, like to like fix the previous issues. Yeah.
What is the testing that they have? Like, what does the testing that they do for condition variable to make sure that it kind of works?
Yeah, they have tests. They have.
I hope so.
Yeah. No. I did break their tests a few times while doing this work. So like when I made buggy changes, like some tests would break in glibc. So like there's definitely tests there that like, I don't know, they have it's I don't know how many. Let's say it's 20. They have like 20 different tests that like exercise condition variables in various ways. Yeah. Yes.
Did you happen to look up tests for other condition variable implementations, like outside of glibc, and then try to run them on this, see if they break?
I did not try that. No. Cool.
We'll have to have some semantic for that.
I mean, the interface is always the same, right? Like they all follow a standard interface, condition variables. Cool. But yeah, we're at time. Cool. That's it. Yeah. Yeah, I tried earlier to find out like what happened to Frank Barris, like why did he stop showing up? And it's like, I don't know. It's
open source. People always stop showing up. Like
yeah, of course, but like
Maybe he never got the signal.
yeah. But like he posts lots of.
I am having a harder time understanding why you kept showing.
I know. But like yeah, like he posts like this thing where he finally explains like his patch in lots of detail, and then like nobody responds and like nothing happens, and 3 months later some other random person comes along saying like, hey, our .NET Core application is freezing quite regularly, like saying like, no, this is really a bad bug, but like this is the last time Frank Barris shows up, and like nothing for 3 months, no response, just some other person coming in like, please fix this bug. So I don't know. Yes.
Wait, so could they have like mitigated this bug by randomly like trying to detect deadlocks and then signaling one of the?
Yes.
Yeah.
That was one thing we considered. It's just like randomly add more signals.
Yeah.
Or just like, because spurious wakes are allowed anyways, and so you just like have another thread that once per second like signals. Yeah. We considered that, but we switched to a different condition variable instead. But yeah.